Worksheet 6A elastic torsion. If a 4-inch diameter steel alloy, 4-inch, and they give us the yield shear stress, dy 51 ksi, and G modulus of rigidity 11,000 ksi. The member is loaded as shown. Draw a taut diagram for the member. Determine the magnitude and location of the maximum shear stress in the structure, and determine the angle of twist of the free end with respect to the fixed end. So let's start with the part number 1, and part number 2 will be the design we will discuss later on. So first is always find the external reaction. As you can see, this is a cantilever with the fixed support on the left. We want to know what is the external reaction, in this case the moment, the torque that have in the fixed support. So from here we can draw the external the forces to determine the external reaction or external forces. External forces or reactions. So reactions. So we can draw the free body diagram for the whole shaft. Free body diagram for the whole shaft. So put here whole shaft. At that, and the actual axis is x. That is x, and we have ABC, so we can have 8, 6, and 4. 8, 6, 8 feet, 6 feet, and 4 feet for D, C, B, and A. And at C we have a negative external torque. Why negative? Use your right hand rule. So this is foot kips, and then as B we have a positive, and that is 10 foot kips, and at A we have a negative torsion based on the right hand rule. How is right hand rule? Use your right hand, make the thumb go to the positive x-axis. Whatever the other four fingers rotate, that will be the positive torsion. So this is 4 foot kips. And from that we have a reaction at D, and that we call it TD. Reaction TD. So from that one, if we take moment about the longitudinal axis, so with the x, so we have sum of all the moments, about the x-axis, and assume positive in x direction, right? Positive based on the right hand rule. So if you have x here, x-axis, then it based on the right hand rule. So from that we can have TD is positive. See, TD positive, then negative 11 plus 10 negative 4 equal to 0 for equilibrium. From that we will have TD equal to in this case positive, so it's same as our assumed direction, so plus 5 foot kip. So that is the external reactions at the fixed support D. So when you find out the external reactions and forces, we can go ahead to find out the internal torsion for each portion of the shaft DC, CB, and BA. Okay, so let's cut each of them and then find out the internal torsion, because as you can see there is three portions that have different torsion there: DC, CB, and BA. So let's find out the internal forces. In this case, to be more specific, we talk about internal torsion. So for internal torsions, we first cut through DC, the member DC. So we will have that member here, and then cut DC point D, and as you can see between D and C, so we can have continue that it will be point C there. So but we cut somewhere in the middle, and we have the torsion TD already have. TD is 5 foot kips, 5 foot kips, and we want to find out what is the torsion, internal torsion in the segment DC, so that we'll have a DC. So from that, as you can see, we can have sum of all the moment about X, and assume positive go through X as well. So we can have with the right hand rule, and then we have 0, and it equal to 5 negative DC also x-axis, so it will be TDC, negative TDC, because that is based on our assumption that is negative TDC. From that we have TDC equal to 5 foot kips, 5 foot kips, and it positive based on our assumption, and if it right hand rule, then it will be negative, right? So our assumption on the free body diagram that either negative based on the right hand rule. I say it again, if we put your right hand, the thumb go to the X, whatever the rotation of the other 4 fingers, that will be the positive torsion. So from that, if we follow the right hand rules, so we have TDC equal to negative 5 foot kips. Okay, and then we can continue to do for portion BC, CB. Then we can continue for what is the internal torsion in member BC. So we have D here, we have C, and if we continue, we cut somewhere between C and B. So we have that B. From that we have at D, we have a reaction 5 foot kips. I put K to make it easy. And at C, we have 11 foot kip from there, right? So it will be 11 at C, 11 foot kips. So cut somewhere between C and B, we call that in the internal portion, and let's assume now it's positive based on the right hand rule, so that it TCB. So from that we can have sum of all the moment about x, assume right hand rule, positive right hand rule is the positive for that equation. So we have 5 negative 11 plus TCB equals 0. From that we have TCB equal to 6 foot cubes, and it also right hand rule with positive 6 foot cubes. 6 foot cube. So put positive there for right hand rules. Now we still have one more which is BC. So let's continue to draw the free body diagram for the cut between B and C. Between B and C. So we have here we have D, we have C, we have B, and somewhere if we continue it will be A. So that is A. So we have at D we have 5 foot cubes. At C we have 11 foot cubes. At B we have 10 foot cubes. 10 foot cubes. And as we cut before 8, if we cut before 8, then as you can see the 4 foot cube in here will not appear in the left side of our cut. If you cut to the cut between B and A and you consider the right side of the shaft, then only the 4 foot cube will be exposed. Keep that in mind. So from that we can assume TBA, and in this case we assume it in the negative based on the right hand rule in our diagram. So from that we can do exactly the same sum of all the moment about x, assume positive in the right hand rule. 0 equal to 5 negative 11 plus 10 negative TBA. From that we can have TBA equal to 15 11, so it will be 4 foot cubes, 4 foot cubes. And based on our diagram we assume it negative based on the right hand rule. Then as you can see the answer is positive, it means it's negative based on the right hand rule. Right hand rule, we have TBA equal to negative 4 foot cubes. So when we have all of that, we can go ahead to do the first portion, which is draw the taut diagram for the member, for the shaft. Draw the taut diagram for the shaft. So let's do that here. The diagram is show the how the torsion, internal torsion for each portion of the shaft. So let's write down the taut diagram, so which is part A, and I also want to follow right hand rule. So along the shaft we have the x-axis, and we have A, B, C, D, A, 8, 6, and 4. So we have point D, we have point C, point C, point B, and point A. Point C, point B, and point A. And from that, based on what we do, we start from D and TDC is 5 foot kips, and in TDC right hand rule, as you can see, it's -5, so we can use the positive going up and negative going down. So from there, as you can see, we can draw that is 5 along the DC, that it will be in terms of the foot kips, right? Internal torque, that here, internal torque. And it should be in foot kips. That internal torque. Let's erase that a little bit and put it closer so it's not confused. TCB. Foot kips. So as you can see here, 5 for segment DC, and then CB 6 positive, so it jump up to 6. Jump up to 6. Let's see here. So it will be 6, and then throughout the CB it will be 6. Let me put it in the middle. So 5, and that is 6, and it's negative for 5 and positive for the 6, and then it go to 4 foot kips TBA, so it will be negative, so go down 4 and it go the whole thing in there, so it will be 4 foot kips. So that, as you can see, so the diagram, the torque diagram, and as you can see here, it have to be consistent. In this case, I go from left to right, or from left to right. You cannot do one segment from right and the other segment from left. That will change the sign. The magnitude will be the same, but it's not consistent in the sign of the torque, positive, negative, based on the right hand rule, etc. So keep consistent in this case. As you can see, when I cut from left to right. If you want, you can cut from right to left consistently. So that is torque diagram part A, and the part B in part 1 of worksheet 6A is determine the magnitude and location of the maximum shear stress in the structure. So as you can see from diagram, and the equation, we can be able to find out where is the maximum shear stress. So let part B here, the first diagram, and then the second, maximum shear stress. And note at J, this is same cross section, so let me make a note here. Note J, the polar moment of inertia, and C, the radius of the shaft, constant for the shaft, constant for the shaft or the member. Then what do we have? We have the shear stress max, tau max, maximum tau at the maximum torque, internal torque. Maximum internal torque. And why is that? If you recall, go back to the note we have last time. And for the shear, as you can see, with the equation of the torque, so the torque equal to, with the tau, which is the share, equal to T over J rho. So it will be maximum tau when we get T. The torque will be maximum because it directly proportional to T. The share stress tau directly proportional to T and directly proportional to the rho, which is the radial distance. So it will get a maximum when the torque T capital maximum and the rho is maximum. So what does that mean here? Maximum internal torque T is maximum, which is at CB, right? You see magnitude wise, the torque between C and B are 6 foot cubes from the torque diagram. DC only 5, BA only 4, so it will be at there. So from that we can find out the T max, tau max equal to, from that equation just show you earlier here, tau equal to T over J rho. So let's go back to that equation. We can have a T max, torsion max. Again, we have to do the rho max, which is the radius, divided by J, the polar moment of inertia. And from all of that, we already know we can have sig tau max, 6 foot cubes. Then it need to be inch, and you can see everything is KSI, etc. So we have to change that to inch. So you have to time 12 inch over 1 foot. So it will be 6 times 12, 72 inch cubes. And then the shaft here, the radius, the diameter is 4 inch. Then the radius is 2 inch. So 2 inch. Divide by J, and we already talking about in that lesson 6, polar moment of inertia. This is a solid circular section, pi over 2 C4. Pi over 2 C4. Go back. Pi over 2 C4. So we have it pi over 2 C, in this case 2 inches, power 4. From that we will get 5.72 KSI, and have to be between B and C, and on the outside, right, on the outermost fiber of the shaft, because we talk about C, not in the center. Even at BC, between B and C, but in the center of the shaft, then the tau is still 0, because as you can see, T tau max equal TCJ. So C, we talk about the outside, the perimeter of the cross section. If we even in BC, but if we have rho, the radial distance, we put it 0, which is in the center of the shaft of the cross section, then tau is still 0 at BC. Keep that in mind for the maximum shear stress. So that we have for the tau. And then the next question that we have in that part, before we conclude and go to the next video for part 2, determine the angle of twist of the free end with respect to the fixed end. So free end is A, with respect to fixed end is D. So let's go to that. Here, next, the angle of twist. So we already know for each of them in each portion. So we have 5 of A relative to D, which is the free end relative to fixed end, equal to 5 for each portion. AB plus 5 BC plus 5 CD for each segment of that. And each segment of that we have, for 5, we know how to determine that 5 equal to TL over GJ, that in lesson 6 we have here. So from that, plug in here, we will have TL over GJ for portion segment AB plus TL. I suggest you to use like that slowly for each portion before we plug the number in. Otherwise, we mess up with the answer because sometimes they give different material, different geometry of cross section, etc. So CD. So from that, we can now plug in for each portion. So now we have 5 AD, which is the angle of twist of A with respect to B. And as you can see here, the torsion this is the same shaft, so the same material, so G the same, which is the modulus of rigidity, and J, the shaft here is not changed in terms of the diameter, so it will be the same for all three segments A, B, B, C, and CD. So that the denominator will be the same. So we can plug in with the denominator, which is J and G, right? So J 5/2 C4. In this case, we can plug in that is 2 power 4. And then we have G. The problem gives us 11 KSI, 11,000 KSI. So we can plug in 11,000 KSI times 11,000 KSI. And then the top one, TL. For AB, it could be 4 gives, that's T, right? Give foot. And then 6 at CB and 5 at DC. And the L, it will be given, you see, 8 inches, 6 inches, and 4 inches, based on the problem they give us there. Oh, feet, 6 feet. 6 feet. So we have feet. So plug in with changing the unit. It's very important here. So what do we have here? We will have 48. So T will be 4, and it's -4, as you can see there, -4. So we plug in T -4 times 4 with 12. So we can have 48 inches plus TL for BC is +6. So we have 6 times the distance, 6 times 12, which is 72 inches. And then plus CD, TE5, negative. So you put -5. And then CD, the L, the length, 8 feet. So it will be 8 times 12, which is 96 inches. Have we done with the unit conversion? Not yet. 4 foot cubes, 6 foot cubes, 5 foot cubes, -4, +6, -5. That is foot cubes. Everything here, as you can see, inch. So we have to convert that into inch. Similar to do it in here, 12 inch per foot. So from that, we have to time outside 12 inch per foot when we convert the torsion from foot cubes to inch cubes. From that one, we can have 5 AD equal to -1.042 10 power -2, and the angles have to be radians. Angle have to be radian, and it, as you can see, it should be a very small angles, and that is the answer for part C in this equation. Answer. So very small, and what does negative mean? It means that the angle of twist with at A with respect to D is opposite to or negative based on the right hand rule. So it means that if you put your right hand up, your thumb go to the x-axis, whatever the opposite of the other forefinger go, that is the angle of twist that go. Okay, so that is the negative based on the right hand rule there. So with that, we done for the part number 1. The next part is about design of the shaft. For this worksheet 6A, it should be easier and will be short.